This lecture is on Section 3.1 from Math 311, a course in linear algebra at Western Illinois University. So we're going to talk about matrix operations, and we're finally going to give an official definition of a matrix, even though we've been working with them for the last couple of chapters. A matrix, of course, is just a rectangular array of numbers. These numbers are usually real. Okay. And to be more specific, an m by n matrix, A, is just a matrix consisting of m rows and n columns. Okay. And so a matrix, we can describe it like this, or we can also describe it by describing a typical entry. This A sub ij is a real number that represents the number that's in the ith row and jth column of the matrix. So we call that the ijth entry. So we can describe it this way if we don't want to write down all of them, because a lot of times the matrices can be quite big. We take two matrices are equal only if they're the same dimension and all the corresponding entries are the same. So that means if they're both m by n matrices and A sub ij equals B sub ij for all ij. And then there are some special, quote-unquote, special matrices. A square matrix is exactly what it is. It's a square where the number of rows equals the number of columns. We have for every square matrix, we have an identity matrix of that size, and that consists of ones on the diagonal and zeros everywhere else. Okay, and of course by diagonal we mean the ij entries where I equals j. So the identity matrix consists of just all ones on the diagonal and zeros everywhere else. This we call I3. It's a 3 by 3 identity matrix. Sometimes we'll denote this I2. It's a 2 by 2 identity matrix. And we're going to see it in a little bit there why they're called the identity matrix. Diagonal matrices. In these matrices, all the non-zero elements are on the diagonal. Of course, we could have zeros on the diagonal too, but anything off the diagonal is zeros. An upper triangular matrix, anything below the diagonal is all zeros. With a lower triangular matrix, all the anything above the diagonal is all zeros. Okay, so we'll see these particularly the upper triangular matrix will have a role later on when we talk about eigenvalues and stuff like that. All right, so pretty straightforward what a matrix is. Now we're going to talk about a number of operations we can do on them. The first is matrix addition, and this is very easy. It's almost as easy as vector addition, where we just take if A and B are two m by n matrices, then their sum is also an m by n matrix, and we get the entries just by adding the corresponding entries in A and B. So, for example, if we want the here we have two by two matrices, to add these, we just add the corresponding entries. We get 1 plus 6, that's 7. 5 plus 0 is 5. Negative 7 plus 5 is negative 2. And 2 plus negative 4 is also negative 2. Okay. All right. So here we have here we have a 2 by 3 matrices, and if we add them together, we get 0 plus 7, 6 plus negative 5 is 1, 10 plus 9 is 19, then 5, 4 plus 8 is 12. And 2 minus 4 is negative 2. Okay. All right, and here, in this case, here we have a 2 by 2 matrix, and here we have a 2 by 3 matrix. There's no way we can add these because they have different dimensions, so this is a bit of a trick. This is undefined. Okay, just like you can't add two vectors of different lengths, you can't add two matrices of different dimensions. Okay, next is scalar multiplications of matrices, where it's very similar to scalar multiplication of vectors. If C is a scalar, that is a real number, and A is an m by n matrix, you just multiply all the entries by C, and you get this new matrix C times A. So this would be, just here you're just multiplying all the entries by 3. So you get 3, 12, negative 15, 0, 6, 12. For this matrix, you multiply everything by negative 2, so you get negative 2, negative 12, 0, negative 10, negative 4, negative 2, 2, negative 6, and negative 14. Okay. If I haven't made any arithmetic mistakes, which I often do. You can do with scalars can of course be fractions as well, so this would be 5/7, negative 1/7, 3/7, and 7/7, which is 1. Okay. All right, so that's that's scalar multiplication of matrices. Nothing terribly hard there. The hard part, or the interesting part of this lecture, or these operations, is matrix multiplication. This is where this is very counterintuitive the first time you see it. You would think, like, if to multiply matrices, you just multiply their corresponding entries, but that's not how it works at all. And in fact, we're going to see there are some matrices you might have two matrices of the same dimensions, and you might not be able to multiply them at all. So the way that works is, if A is an m by n matrix and B is an n by r matrix, then the product AB is an m by r matrix, such that the ij entry is really the dot product of the ith row of A and the jth column of B. Okay, we can also write it this way, where you can do this. I think it's a lot easier. Just remember, you would take the ith row of the first matrix, the jth column of the second matrix, and you take the dot product. And to do that, basically, the only way you can this product makes sense is if the number of columns in the first matrix is equal to the number of rows in the second matrix. Okay, so basically, you have to have an m by r and or rather an m by n and an n by r. Okay, so these have to be the same, and then the outer numbers here, those are going to be the dimensions of your resulting matrix. So in this case, in this first case, we have two 2 by 2 matrices, and to get we have a 2 by 2 and a 2 by 2. Okay, we have 2 rows here, or rather 2 columns here, 2 rows here, so we're fine. The resulting matrix is going to also be 2 by 2, and what we'll do is we get the first entry, we get the first row, first column, we get 1 times 5 plus 2 times 6. First row, second column, 1 times negative 3 plus 2 times negative 2. Now we go to the next one. Second row, first column, that's 3 times 5 plus 4 times 6. First row, second row, second column would be 3 times negative 3 plus 4 times negative 2. Okay, and then this becomes 5 plus 12, that's 17. Negative 3 plus negative 4, that's negative 7. This is 15 plus 24, which is 39, I think. And then negative 9 plus negative 8 is negative 17. All right. Now, let's switch these matrices around and see if we get the same results. And spoiler alert, we're not. Here, in this case, first row, first column, we get 5 times 1 plus negative 3 times 3. Okay. Well, already we can see that this is going to be 5 minus 9. That's going to be negative 4. So already we know that this is going to be different. Then we get 5 times 1, or I'm sorry, 5 times 2 plus negative 3 times 4. Then 6 times 1 plus negative 2 times 3. Okay, and then 6 times 2 plus negative 2 times 4. Okay, so this is going to be negative 4. This is going to be 10 minus 12, that's negative 2. This will be 6 minus 6, that's 0. And here we have 12 minus 8, that's 4. Okay. These are not equal. Okay. And in general, A times B is not equal to B times A. Okay. The fancy word is we say they're not commutative. Okay. Let's look at this next example. Here we have a 2 by 2 matrix, and here we have how many rows? 2 rows, 1 column. Okay. All right. These agree. Our result is going to be a 2 by 1 column as well. And what this will be is 1 times 5 plus 2 times 6. And then this will be 3 times 5 plus 4 times 6. And this will be, again, 17 and 39. And you'll see it's no accident. It turns out there's no accident that this column is the same as the column up here. Because basically we were just doing the same operation, the first couple operations we did up here. Let's look at this one. Here we have 1 row, 2 columns. Here we have 2 rows, 2 columns. And in this case, we should get a 1 by 2 matrix. And we can check, this is going to be 5 times 1 plus 6 times 3. And then the next entry will 5 times 2 plus 6 times 4. So this is going to be 5 plus 18, that's 23. And then this will be 10 plus 24, that's 34, I think. Okay. So again, we'll have 1 row, 2 columns, and that's our result here. This next one, we have a 3 by 2, 2 by 2. So our result will be 3 by 2. And I'm going to leave it up to you to check. Maybe you can pause the video right now. But the result will be 2, 1, 4, 11, and 7, 8. Because this is going to be, again, the 3 by 2 is going to be the result here. Let's look and see this with this next example. Here we have 2 rows, 1 column. 1 row, 2 columns. So believe it or not, this will be actually, our result should be a 2 by 2 matrix. And let's see what we have. Well, the first row, in this case, the rows and the columns just consist of one entry. We have 1 times 3, okay, then 1 times 4, 2 times 3, 2 times 4. So this will be 3, 4, 6, 8. This next example, this is 2 by 3. This is also 2 by 3. In this case, the number of columns here is different from the number of rows. So there's no way we can multiply this. This doesn't make any sense. So this is undefined. All right. So in particular, one other thing here before we move on. If you take a couple matrices like this, 1, 0, 0, 0, and multiply it by 0, 0, 0, 1, if you check, you'll see that you'll get zeros everywhere. You'll have 0 plus 0, 0 plus 0, 0 plus 0, 0 plus 0. Okay, and so here we have the 0 matrix as a result, but we have the product of 2 non-zero matrices is equal to the 0 matrix. So this is another way multiplication of matrices is quite different than multiplication of real numbers. Okay. All right. Moving on. We can talk about powers. The powers of matrix A squared is just the same as A times A. A cubed would be A times A times A. So I'm going to, let's see what A squared would be. This would be, if A is 1, 2, 3, negative 1, and we multiply it by itself. What will this be? 1 times 1, 1, so we have 1 plus 6 is 7, 2 plus negative 2, that's 0. And then we have 3 plus negative 3, that's 0. 6 plus 1 is, did I do this right? Yeah, 6 plus 1 is 7. Okay. So we have actually set, this is actually going to be 7 times the identity matrix. If I didn't do anything wrong, which I don't think I did, okay. So that's A squared. A cubed will just be A squared, which is 7007 times 1, 2, 3, negative 1. And in this case, you'll see that we have we're just multiplying everything by 7 in this case. When you have a diagonal matrix where all the entries on the diagonal are the same, it really has the effect of just multiplying this by 7, everything by 7. So it's be 7 plus 0, 14 plus 0, 0 plus 21, and 0 plus negative 7. Okay. All right. Now, when you have diagonal matrices, as we can see up here, diagonal matrices make things a lot easier. In this case, A squared is going to be 2, 0, 0, negative 3, 2, 0, 0, negative 3. And this turns out to be 4 plus 0, 0 plus 0, 0 plus 0, and 0 plus 9. Okay. In other words, we got this up by squaring each of these diagonal terms. Now you can get this. This only works with diagonal matrices, because we have a lot of zeros and things just go away. You can check that A cubed is going to be 8, 0, 0, negative 27, because this is 2 cubed, and this is negative 3 cubed. And then A to the fourth, you can check, will be 16, 0, 0, 81. Because this is 2 to the fourth, this is negative 3 to the fourth. Okay. I'm going to let you find out what these are. In fact, this time I'll pause the video and let you work on this.